Section 5.3, angle bisectors of triangles. We're going to use the angle bisector theorem and its converse to find missing information. So let's just review angle bisector for a minute. An angle bisector, remember, is a ray that divides an angle into two congruent adjacent angles. So here, AC, ray AC, is the angle bisector of angle DAB. Now, another thing we need to talk about is when we talk about the distance from a point to a line. So if you look at line AD that I've drawn here at the bottom, and we look at point C, the distance from point C to the line is always going to be the perpendicular segment. Because otherwise, if you draw any other line, you could have multiple different distances. So we always talk about the distance from a point to a line has to be perpendicular to that line. So just keep that in mind moving forward because we're going to talk about this some more. So in this particular case, we have point C is actually on the angle bisector right here. And so if we talk about point C, the distance from point C to like ray AB, then that would be this right here, that perpendicular distance. So just keep that in mind as we talk about this next theorem. So the angle bisector theorem says that if a point is on the angle bisector, then it is equidistant from the two sides. So we can see point C right here, and it is on this ray AC, and we can see that it's bisecting the angle. We can see it from the markings right here and right here. So if that is true, if the point is on the angle bisector, then it's equidistant. So that means from the distance from point C to one side of the angle will be the same as from the point to the other side of the angle. So what that allows us to conclude then is that BC, segment BC, is congruent to segment DC. Or we could say that BC, the length and distance, is equal to DC, which means they're congruent. So that's the angle bisector theorem. Well, it turns out that the converse of the angle bisector theorem is also true. So now, again, the converse just switches everything around. The last theorem said if it's on the angle bisector, it's equidistant. This is saying if a point is on the interior of an angle and it is equidistant, so you can see that these distances are the same. If it's equidistant from the sides of the angle, then what that means is it's going to lie on the angle bisector. So what that now tells us is that angle DAC will be congruent to angle BAC. So it allows us to conclude that AC, ray AC, is the angle bisector of angle DAB, and that the measure of angle DAC will equal the measure of angle BAC. So those are the two theorems that we're going to talk about, and this is what we're going to look at some examples. So it says find AD. I want to find this segment right there. Well, if you notice, this is marked the same, or we could use a tick mark, but that means those angles are congruent. So it means that point D has to be on the angle bisector. So then it also means that these two segments would be congruent. So AD will equal 19 units. Okay, in this next example, we can see that, again, we have these marked as the same, so that it means that these pieces will be the same, because it means that this point has to be on the angle bisector, which means it is equidistant from the sides of the angle. So then I set 4x plus 3 equal to 8x minus 9. And now when I move the x's to one side and the numbers to the other, I get x is equal to 3. So I found the value of x. Let's take a look at another example. Again, always look at what is marked and what do you have. So now you can see that these are marked congruent. So what that tells you is that h has to be on the angle bisector. So this is the converse of the angle bisector theorem. So it means these two angle pieces are the same. So the measure of angle EFH would also equal 28 degrees. Next question says find the value of x. Again, you can see that these are marked congruent. So then it tells you that this point is on the angle bisector. Again, using the converse. So again, all we need to do is set these two expressions equal to each other. And then when we solve, we would get x equals 7. All right, well, let's talk about one more thing. In section 5.2, we talked about the perpendicular bisectors all meeting at a point of concurrency in a triangle. Well, it turns out that the angle bisectors also meet at a point of concurrency, and that point of concurrency is called the incenter. So that point right there is called the incenter. And in this case, the incenter will always be on the interior or inside of the triangle, whereas the angle bisector could be inside, outside, or on the actual side. And it turns out it's the center of a circle that could be inscribed. And the reason is because these angle bisectors, these are the angle bisectors right here in yellow. The angle bisectors all meet at a point of concurrency called the incenter. And its significance is that it's equidistant from the sides of the triangle. So what that means is that this distance right here, and this distance right here, and this distance right here are all the same. And again, we're always talking about that being a perpendicular distance. And so because that distance is the same to the side of the triangle, those are all radii of a circle. And so you can inscribe a circle. So the center of the circle is said to be the center of a circle, and the circle is said to be inscribed within the triangle. So if we look at this next example, it tells you that point T right here is the incenter. So if it's the incenter, it is from the angle bisectors. So that means that angle is bisected. That means that this angle and this angle will be congruent. It also means, remember, that this point, the incenter, is equidistant, meaning the perpendicular distance to each side of the triangle are all the same. So now they want us to find ST. So ST is this segment right here. Well, it will be the same as WT. So ST is 15 units. They also want us to find SR. So SR is this segment right here. And you might be thinking, well, how do we find SR? Well, remember, we just got done finding that this is 15. We can see that this side right here is 26, and we are trying to find this. We are trying to find that value of x right here, SR. Well, it's a right triangle, so we can just use the Pythagorean theorem. That 15 squared plus x squared equals 26 squared. So if I take 26 squared and I subtract 15 squared, that gives me 451. So I take the square root of 451, and then x is approximately 21.24 units. All right, we have one more example here. Again, it tells us that point G is the incenter. So it's the incenter, meaning it's equidistant to each side of the triangle. That perpendicular distance is the same. And remember, it also means they're on the angle bisectors, so those angles are all the same. And these two angles are also the same, etc. All right, so we, in this example, want to find DG. So I am going to find DG. How am I going to find that? Well, it's going to be the same as FG. And again, I can use the Pythagorean theorem right here to find FG, and then it will be the same. So I just did this in this last example. So why don't you go ahead and see if you can find it? But we'll just use the Pythagorean theorem. And so x is equal to 5. So this is 5. So that means that DG will also equal 5 units. All right, that is the end of